what is the difference between finite and infinite? And why is finite element method called a successful numerical methods technique? And what does it do? And what are the differential equations? Are those physics equations? Are the differential equations or the governing equations define the physics? So, so what do the governing equations do, and how are the governing equations solved? Okay, so let's look into it. So, what is finite element analysis and what does it do? So, in the two pictures that you look here, there is a spanner, and can you see that there are red spots only in certain regions? Why is that? Is that because of stress concentration effects? Why should stress concentrate only at those regions? So, what if it is red? Does it mean that it might fail? Does it mean that it has crossed yielding? And now let's look at the truck. So the truck looks like it has already crashed into something, and the bumper looks completely damaged. So has it crossed yield? Yes, absolutely yes. There's no doubt about it. And what are the differences between these two images? The one, the spanner, is the static analysis, whereas the truck, it's a dynamic analysis. And the crash would have happened in very few seconds, not even a second, microseconds or less. So, in order to capture that, we need to perform a time dependent analysis. So, in this module, we will be applying finite method to solve structural engineering or solid mechanics problems. And only linear elastic behavior is assumed throughout. What is the difference between linear and non-linear? And what is the difference between elastic and plastic? Is it just the response after you apply the load? Does plastic mean that after you release the load, it can regain its original position? So why is it called linear elastic behavior? So what are the steps in performing FEA? First, discretizing domain, that is meshing. So how many subdivided parts appear and what are these small subdivided parts called? Are these called as elements? And what are these corners of each element called? Are they nodes? So how do you create this mesh? Is it a good mesh? Does it look good? It looks like biased. It's near the circle. It looks like the element size is less. And as you move away from the circle, the element size keeps on increasing. Is it a good mesh? Let's see. And now writing the element stiffness matrices. So does it mean that each of these elements, so how many elements you have here? One, two. So this number into 4. So how much is it? Yes. So let's take just one element. Let's take this element. So you'll have to write the stiffness equations for this element and similarly for all the elements. Now that you have element stiffness matrices for each of these, how many, totally how many? Yeah, for all these elements, you have individual element stiffness matrices. And now you've written that down. It's time to assemble. That's the third step. Let's combine all the individual element stiffness matrices to present the entire domain or structure. This is now called global stiffness matrix. And now this global stiffness matrix has all the elements information together. So this represents the entire domain or structure. And now let's come to applying the boundary conditions like the constraints or loads, or it could be displacements as well. Imagine you're stretching a rubber band. How do you do that? Would you pull the rubber band in both the directions? Yes. Whereas in final analysis, you'll have to fix at one end and just pull from the other end. So one end has to be fixed, and the other end you can apply displacement or force. So now the boundary conditions are it is fixed at one end and pulled or pushed at the other end. Now you have the global stiffness matrix and you apply the boundary conditions. What about the material? Yes, all the element stiffness matrices, they have the material properties as well. So now let's solve the equations. So how do you solve the equations? Or rather, how does the software solve these equations? What are the solvers or processors involved? And once it has been solved, so if you look at the picture on the right corner, what do you see? It has some color plots. And what do they mean? Why is it blue here? And why is it there is a red spot over here? And then yellow, green, and then green, and then blue. So you see, even here you have 4 different variations. Here you have 4 different variations. So, and it is more, and it is so intense or concentrated at this location. You see, what you see here is it is increasing, whereas here it is decreasing. Why is it? So this is how we interpret the stresses or the reaction forces, or the element forces. So what we observe here is on this side, it is subjected to tensile forces or tensile stresses, whereas this side, it is subjected to compressive stresses. And now let's check, does it sound, does it look good? Does it follow the physics? So how would, so what is this? Is this a square plate with a circle? Have you just taken a quarter of the entire geometry? And why should you take just a quarter of the entire geometry? Why can't you take the entire geometry? So post-processing of results, let's see. So you're pulling at one end and you're applying quarter symmetry. So in order to apply quarter symmetry, we fix on both sides. So now it is being pulled at the top and the bottom. So what is happening over here? So on the when it is pulled upwards, the tensile stress is getting created at the center. Does it look good? Does it follow the physics? This is how we interpret, and this is called post-processing. So now, when it comes to stiffness matrices, you have different based formulations. One is direct stiffness method, and the other is energy-based formulation. And then how you assemble stiffness matrices to form the global stiffness matrix. And 2D pin-jointed structures, continuum elements. What are the different structural elements? Shells or plates? And what are the different practical FEA guidelines? So what is the difference between a plate and a shell? So what do you observe here? So it looks like this is the region of interest. There are more number of elements over here, and it's completely dark here, meaning there are a lot of elements, and still there are a lot of elements here. Whereas here and here, can you see that? Here it is denser. Here it is not that dense. You can count easily. So there are three, yeah, seven. Whereas this one you can't count because it is extra fine. So why is it so finely meshed at the region of interest? Is it a FEA guideline? So what you see here is a pressure in the along the axial length. So along the axial length, the pressure is higher only here. and gradually it is decreasing. At this region, it is zero. There is no pressure at all. So this might be at this region profile length. So stress analysis fundamentals. Um, you must be familiar with these already. So let's just have a quick snapshot view. So what is uniaxial or one-dimensional stress and strain relationship? What is strain? Is it change in length by original length? So what is the original length here? Is it L naught? And what is the change in length? Is it U? And now, what is the difference between engineering stress and true stress? So here, engineering stress, as per engineering stress, it is force by unit area, meaning the area is constant. But in reality, does the area remain constant? If you're pulling a rubber bar, or even if it is steel, you would have performed some experiments. In steel bars, steel rods, they fail with a cup and cone fracture. Whereas rubber, you would have experienced it. If you keep pulling it, the diameter at the center or the diameter is going to decrease and the length is going to increase. So the area is not constant. But why is this constant here? Is this a correct assumption to have a constant area? And now there is something called stress state, stress at a point. That is del F by del A. The concept of stress at a point is physically valid because the small area dA would carry a small amount of force dF. So now this is uniaxial stress strain curve. So this is how you'd have performed an experiment, a cylindrical rod in your lab. So it could be a cylindrical rod, or this is a cylindrical rod. So otherwise you can use a dog bone bar or a cylindrical rod, which is subjected to uniaxial tension force. It's only along this axis you have the forces. There is, at one end it is going to be fixed and the other end it is going to be pulled. But this cylindrical rod is subjected to tension. That's why you have one force at the top and one force at the bottom. And what is the elastic region? It is from O until here. And afterwards, you have the upper yield stress. This means that the yielding has begun. And once the yielding has begun, immediately the stress drops down, and that is called lower yield stress. And again, what happens is the stress increases until it reaches UTS. Suppose if you unload at point B, you can recover at least a little. This OC is called as plastic strain. There is a damage or there is a plastic strain which you can't recover. Whereas if you have released the force here, it would have been perfectly elastic and it would have reached O. Whereas OC, there is already a plastic strain here. Again, if you start loading, it will reach UTS, and after a certain UTS is the highest stress, and if you keep on loading, the strain keeps on increasing. Can you see that the strain is increasing constantly? At when the percentage of the area decreases so much and it can not withstand the force, and at that point it will fail. In steel, it is low and medium carbon steel, so it would fail under cup and cone fracture. Check for cup and cone fracture images. You'll understand how steels break. So these are alloy steels. Alloys are better materials. So here, when it comes to alloys, what you see is it is quite better than the normal steels. 0.1 proof stress is taken 0.1 percentage away. So this is